consider an atom that can be in a state phi or a state psi with energies E phi and E psi. And let's say we shine light on this atom. And then it can happen that we make a transition from one of these states to the other and thereby absorb or emit light, and the frequency of the absorbed or emitted light is proportional to the difference of these two energies here. Now, when we are interested in the intensity of the emitted or absorbed light, then we have to look at this matrix element here. So the O, the operator O, is for this light which we shine on the atom, and the initial and final states psi and phi, and then the intensity is proportional to this matrix element absolute value squared. So this is the result of so-called time-dependent perturbation theory. The unperturbed system here is the atom just sitting there without us shining light on it. And if this unperturbed system is rotationally invariant, then this means that our states psi and phi, they transform in irreps of SO3, let's say irreps gamma 2L plus 1 and gamma 2L prime plus 1 of the rotation group. So this is the unperturbed system, and saying that these states transform in these irreps, I mean there are invariant subspaces, irreducible invariant subspaces, and we can introduce some basis where this is one basis vector for such a subspace, and then it can be complemented to a full basis of an invariant subspace carrying this irrep. Okay, and now if the perturbation, so the perturbation here is shining light on the atom, is also rotationally invariant. So it's not only the atom itself that looks the same from all directions, but it also doesn't matter from which direction we shine the light on the atom. Then this operator O also transforms in some irrep of SO3. So it would be one, same as above here, it would be one operator in a set of operators which together transform in some irrep. Yeah? So for short I write O transforms in some SO3 irrep, and if this is ordinary light, it would be so-called dipole radiation, which is relevant here, and then that would be the three-dimensional irrep of SO3. We don't know so much about these irreps yet. They can be labeled by the dimensions, and never mind, we're going to learn this later. So this is dipole radiation. Now we would write something like this. We would say our matrix element here we are interested in now takes this form. There's maybe some L prime and M prime here, and then there's this operator for the perturbation. I call this O3 double prime and L and M. So I label the initial and final states by these irrep labels, and then I'm indicating where in this irrep we're sitting, we're starting and ending, and I also label the perturbation, it's wrong, the perturbation with this irrep label here, and then we say here which one of this set of operators it is we're interested in. So the L's and the 3 are irrep labels. And now the M's, well, the M could run from minus L to L. That's something we learn later. And the M prime from minus L prime to L prime. And the M double prime could be minus 1, 0, or 1. And now some more SO3 representation theory, which we don't know yet, will tell us that decomposing this tensor product here, gamma 2L plus 1 tensor 3, get a sum of 3 irreps. That's gamma 2L minus 1 plus gamma 2L plus 1, gamma 2L plus 3. So if you look at this L label here, then we can say that it's either unchanged as here in the middle, or it's one larger or one smaller. So the change in L has to be 0 plus or minus 1. So this tells us that this thing here is non-zero only if, let's say, L prime minus L is minus 1, 0, or 1. So this is such a selection rule again. And now in this case where it is non-zero, the Wigner-Eckart theorem tells us a little more. So let's write down this matrix element again we're interested in, L prime, M prime, O3, M double prime, L, M. So that's now some Clebsch-Gordon, L prime, M prime, 3, 2L plus 1, that's the rep label, what we're decomposing, M double prime, M. And some reduced matrix element, say L prime, O3, L. So there's just this, for fixed L and L prime, there's just this one number here, which encodes all the physics. And then there are lots of transitions, which we can make, in principle, from different states, labeled by these M's here. They run over all these values. But their relative intensities, they are fixed by the Clebsch-Gordon. So they are fixed by representation theory. All the physics is this in this single reduced matrix element.